A denote a finite dimensional k-algebra, and here algebra means close to the minimal, I think the minimal thing it could possibly mean. Algebra means there is a bilinear product. And this is not assumed to be commutative or unital or even associative. Later I may specialize, in fact I will specialize to the unital case, but much of what I say holds in, it's just that the examples are unital, but everything really holds without even that assumption. Or you can also impose extra structure. For instance, you can consider algebras with involution. But at the outset, A is just some set with some vector space with the multiplication. Throughout, we'll write G for the automorphism group of A, and this is the automorphism group of A as an algebra, and G is a linear algebraic group. By the term K-ring, we will mean an algebra that is commutative, associative, and unital. So algebra is as badly behaved as you want, and K-ring is taking us back into the bounds of commutative algebra. If R is a K-ring, then I can define the concept of R form of A. This is an R-algebra. And I know I haven't defined at this point an algebra over a non-field, but the definition is the same as for a field. So an R form is an R-algebra B such that there exists a faithfully flat map R to S of rings such that there is an isomorphism S tensor over R with B. It becomes isomorphic as algebras to S tensor over R with the trivial form, which is R tensor over K with A, or really S tensor over K with A, if you like. So the R form B of A is an algebra over R that becomes isomorphic to A after some faithfully flat base change, or extension of scalars, if you prefer to think that way. Okay, well, I think down here I have a table of examples. Let's see, zoom out. I prepared this earlier. Here are some key examples of the concept that I would like to refer to through the talk. For instance, because I'm working in this non-associative, well, this non-unital in particular situation, I can make an algebra that is Kn over K and give it absolutely no multiplication at all. The multiplication is just the zero map. That is to say, A is really just the vector space with no extra structure. And in this case, forms of A turn out to be just rank n projective modules, and the automorphism group is the general linear group. That's a basic and motivating example, in fact. A second example is when Kn is given the obvious component-wise operations. Now it's unital and associative and commutative, and now forms are étale algebras. In this case, G is the symmetric group. And perhaps my favorite instance of this is when the algebra is matrix algebra of side length S, in which case the forms are the Azumaya algebras of degree S, and the automorphism group by the Noether theorem is the projective general linear group. And then below that, I've listed two more examples, which are examples of algebras with involution, which have forms, which are algebras with involution. And there are many instances of this notion of form. I just want to highlight these three in particular. We may meet some more in the course of the talk. Let me mention, in all cases, use n to denote the dimension over k of a, which is why the matrix algebra is written matrices of side length s. The dimension is s squared, which is n. When I say there are many cases of this phenomenon, I'm not lying. Gordeev and Popov in 2003 proved that every linear algebraic group appears in this way. So every linear algebraic group G is aut k-alg A. In fact, for some simple algebra A, at the cost of, potentially the A's that appear here are going to be wildly non-associative, for instance. So let me say, well, just to highlight, this means that there have to be just all sorts of crazy algebras, and forms of them are they're just going to cover all of linear algebraic group theory in some sense. So let me now say that, supposing I have some elements B1 through BR arranged in an R-tuple, then let's say that they generate B, if the obvious thing is the case, if no proper subalgebra of B contains B1 through BR. And let me write gen RB for the cardinality of the minimal generating set, or the minimal generating tuple. And here I mean minimal simply in the sense of cardinality. I'm not saying that a generating set contains, I'm not saying anything about containment of one generating set inside another. I just look for the smallest number of elements that can generate the algebra. So here's the fundamental question of this talk. How big can gen RB be for a fixed A? Here you allow R and A, sorry, I take back, R and B vary So you allow R and B to vary, and you ask, what's the most complicated, in this sense, form of A can you make? And a secondary question, also interesting. Well, actually, before I get to the secondary question, let me state the following. We get a clean answer to this over C, at least. And I think similar results are true for other fields. If G is not unipotent, examples then exist where this quantity becomes arbitrarily large. Sorry, there's a word missing here. Now let me get to the secondary question. How big can gen RB be if the Krull dimension of R is bounded above? So in the examples where the gen B is heading off to infinity, the rings R also have to be, well, they have to be growing in dimension. And there's a question of really of how quickly gen B can grow as the dimension of R grows. Let me mention that the theory of versal objects says something about this. Shows that if we constrain R to be a field over K, then gen RB will be bounded in the way that I've set it up. Okay. So you do need, yes, you certainly do need to allow the dimension of R to head off to infinity to get more complicated examples. So here's a good example, a motivating example. This example is due to Chase, but it appears in a paper of Swan in 1962. So I take R to be the following ring. This is over the real numbers. Polynomials in d+1 variables. And then I mod out by the equation of the sphere. And then I take Z mod 2 fixed points. So here Z mod 2 acts via sending xi to minus xi, as you might expect, I suppose. Here, of course, R is related to the coordinate ring, really, of RPD. Is that right? That's right. So there's some topology underlying this. And then you can prove that for all n, there exists a finitely generated projective R module. Call it Pn of rank n, and it requires at least n plus the dimension of R generators. This is n plus d generators. So this is an example to show that in this particular instance, where the algebra is the stupid algebra, where with only zero multiplication, that forms exist requiring arbitrarily many generators. And you see that indeed, to make the number of generators increase, it is necessary to make the dimension of the ring that the form is defined over also increase. And basically the point of the talk is to repeat this for different A as best as we can. So to get going on that, let me introduce some varieties. So A superscript R, well, that's just R copies of the algebra. And I'd like to point out that that is an affine space over K of dimension Rn, because A is just a vector space, so I can identify it with An. And then inside there, U sub R, and this does not really relate to the unitary group. It's not the unitary group at all. Perhaps it's badly denoted, but here we are. U R inside of A to the R. This is the variety of r-tuples. That generate A as an algebra. That is to say, generate in the sense that I defined earlier. UR is open in AR, which is good, and for R sufficiently large, UR is dense. Well, it's to say, same as to say non-empty. So I will also define, though I won't use it until quite close to the end, Z sub R, which is the complement. And I will call this the bad locus. This is the locus of non-generating tuples. A, and therefore A to the R, and in fact also UR and ZR, they all carry a G action. So G is the automorphism group of A, and therefore it acts on diagonally on A to the R, and that action restricts to an action on UR, and even better, the G action, the action of the automorphism group on UR is free. And the reason the action is free, I'll just say out loud, is that if some non-trivial element of the group were to fix some tuple in UR, then it would have to fix the algebra generated by that tuple, which is all of A. But the element was assumed non-trivial, so that can't happen because G is exactly the automorphism group of A. And when I say free here, I guess that argument maybe just at first blush shows that it's set theoretically free, but it's a scheme theoretic statement. Scheme theoretic stabilizers are trivial. Now, suppose B over R is a form of A. Then we can produce an associated G-torsor T over spec R. And here T is defined as, well, this is the usual thing. I guess T is perhaps being defined in the category of FPPF sheaves, but in practice, in the cases we're looking at, because we're in characteristic 0, everything is smooth, and well, T is going to turn out to be a scheme. So let me give my first.
Should that be isomorphism of R algebras?
Did I miswrite? Yeah, thanks. Thank you, Zenobi. So here's the first theorem.
You may want to tensor A over R.
Oh, it's a nightmare.
Sorry.
Very helpful. It's great to have co-authors who are looking out for you. This is what I want. So there's a natural bijection between the following two sets. On the one hand, you have G-equivariant maps between T and U sub R. And in the cases that we're looking at, this is a map of schemes. And that's one of the sets, the set of these G-equivariant maps. And the other set is the set of r-tuples, B1 through BR in BR that generate. So this allows us to get a geometric handle on what it means for a tuple to generate. Here's the idea underlying the proof. It's I don't think very difficult. So if B is say R tensor A, if this was trivial, then well T would be just spec R cross G, and the bijection is tautology. The whole thing is set up exactly. You can see that that's exactly the two sets are the same, and then one proves that both sets satisfy the right kind of FPPF descent. So you can reduce to the case of a trivial form. Let me make a remark here that's not really a corollary of the theorem, but the theorem highlights it. If every G-torsor over every affine that you see is trivial, if you never see non-trivial G-torsors, then all forms of A are just A again, and so they can be generated by a known number of elements. Just have to find a basis for A, essentially. So if every G-torsor that you see is trivial, then the size of this set is bounded. So for instance, if G is unipotent over C, then gen RB is bounded by some quantity. So the answer to the main question has to be, well, Gen B cannot head off to infinity if the group is unipotent, and we know that every linear algebraic group can appear, so certainly unipotent ones can. So in some cases, the answer to the main question in some sense is no, but that's actually the only case, as we'll see in a bit. Here's a corollary of the theorem that I'm fond of. The quotient UR modulo G represents the following information forms of A equipped with a generating R-tuple. And this is up to isomorphism of all that data. So if like me, you prefer to think of schemes through the functor of points formalism, then you might ask, what is UR mod G? And well, here's the answer. And this describes a lot of quite interesting schemes, in my view. Okay, so let me give a second theorem. And for this theorem, I have to take k to be the complex numbers at present. Suppose G is not unipotent. Then for all positive I, there exists a ring. I may have a C ring, it's a ring over C, of Krull dimension this part is perhaps not the most important, but I'm stating it anyway. I can actually put an upper bound on the Krull dimension of the example that I'm producing. So it's 2 times I, which was chosen, and n, which is the dimension of A, plus some constant term that depends on A but not on I. And there exists an R form B of A such that this form needs a lot of generators. So that answers the main question and to some extent the secondary question. It shows that as long as the group is not unipotent, then you can make this gen B be as complicated as you like, or as big as you like. The rest of the talk then is going to be dedicated to the proof of this theorem.
Sorry, could you say something about, like, I mean, what you know about how sort of optimal this is?
I'll say something about the optimality towards the end. The truth is that in general, I don't know that I don't know. It might be optimal in some cases, but in every case I do know, I'm pretty sure it's completely non-optimal, wildly non-optimal. But I'll say something about that at the end. That is to say, I assume you're asking about optimality. Could I make this R even smaller? And the answer is almost certainly in any particular instance, yes.
Even sort of like, is there some sort of crude bound the other way? I mean, I don't know.
Oh, for a lower bound? Yes, that's the second, or actually really the first part of the project. And I'm talking about this manufacturing bounds. I may also say something about that at the end as well. We know that there's yeah, let me treat these questions at the end, if that's okay. I'd like to say some things about the proof of or the construction really in this theorem. So to do that, I'm going to talk about equivariant cohomology. So this is Borel equivariant cohomology. I just want to introduce a little bit. So again, remember, I'm taking K to be C, and we fix A and G.
We can't see the writing again.
Oh dear. Thanks. That's we good? Or at least we hope so. Okay. So thank you, Zenobi. The writing back.
Yes.
Yeah, we can see it now.
Great. So we can produce a map of spaces. These are topological spaces, e.g. to bg. So I know I haven't produced either of the spaces, but I'm saying we can produce two spaces and a map between them that has the following properties. It's a G-torsor, and if you're squeamish, G here is G of C with the analytic topology, I guess. And if you prefer the term principal G bundle, then this is a principal G bundle. Second, EG is contractible, so it is homotopy equivalent to a point. And third, EG and BG are CW complexes. That's just to rule out pathologies, so let's ignore it. Now suppose X is some space, for instance, a complex variety. Suppose X is a space with a G action. Let me define an equivariant cohomology theory, H sub G X with integer coefficients, but the coefficients may change. They're not the important part of the definition. As the ordinary cohomology of a quotient construction. So here, G acts diagonally. So this is a construction of an equivariant cohomology theory. Let me say some things about it. These are the properties we'll use. This is contravariantly functorial. For equivariant maps. It takes homotopy equivalences. To isomorphisms. And so all objects all x's with a G action, they map equivariantly to a point. You discover that HGX, I'm going to omit the coefficients. If I don't write them, you can assume maybe that they are the integers. So this cohomology is naturally a module, actually in algebra, but it's a module over the equivariant cohomology of a point. So we write Well, sorry, let me write one more thing. If x to x mod g is G torser, then the cohomology, the G equivariant cohomology of x is isomorphic to the cohomology of the quotient space. I think those are the properties of this I'm going to use, and I will write, using the last statement, the equivariant cohomology of a point is the same as the ordinary cohomology of the classifying space BG, and certainly, and this is sometimes what's called the group cohomology of G, particularly if G is a finite group. I need a lemma about this HBG. So G is assumed linear algebraic group, potentially disconnected. And here's my lemma. Unless BG is unipotent, then there exists some rho G depending on G.
I think you mean G is unipotent.
Yes, unless G is unipotent, thank you. Then there exists some rho G such that for all I, at least one of the following groups is non-zero. So I've got this bound on the longest possible gap in the cohomology of G. Let me say a small word about the proof. First of all, it suffices to consider G modulo its unipotent radical. That has the same cohomology, so we can do the calculation, assuming the with this group instead. And there are two cases to consider. The case of a finite group. In this case, work by Benson, Carlson, and Robinson, three sons, in 1990, produces rho G. And this is the worst case because for a general finite group, I don't know of any bound on what rho G can be. It exists, but if G is some complicated finite group, then potentially rho G might be very large as far as I know. But it exists. And then another case that you can reduce to the other case is that when you're looking at an infinite reductive group, in this case, there is a maximal maximal torus. That's non-trivial, and you can use that to produce cohomology classes. So this is classical, I suppose, using a result of Chevrolet and Eilenberg. We can produce classes. There's a lot of them here. Produce classes in H4L for all L. So there have to be non-zero classes with a gap of at most 3 zeros between them. Okay, so now let me attempt the proof of theorem 2 with this lemma. So first of all, ui mod g, as far as we know, so this potentially might not be a variety because it may be only an algebraic space, but it is a manifold. And it's a manifold of dimension I dim a, or in, minus the dimension of g. And as a consequence, this equivariant cohomology group, again I'll omit coefficients, this has no cohomology in degrees sufficiently large. The cohomology has to run out eventually. 2 I dim a minus dim g minus 1. Actually, I don't think that minus 1 is correct. Let me omit it. So that's good. By contrast, by dilemma, we know that BG has cohomology all the way up. So we can find some L, which is less than twice this quantity. Oh, so sorry, less than this quantity I had up above, plus the rho G coming from the lemma. We can find this L where the following two things happen. The cohomology of BG is non-zero, and the cohomology of G equivariant cohomology of UI is 0. And we're going to use this to produce the form, but it's a bit of a journey, so bear with me. We can find some torsor V to V mod G, where both objects here are quasi-projective varieties. And where HL V mod G, the natural map from HLBG to that is an isomorphism. So you can find some V to V mod G that approximates EG to BG in this degree. Then replace V mod G by spec R prime to VG. So I'm going to replace VG by an affine variety. So this is using Joannalu's device, which is a trick for replacing a quasi-projective variety by an affine one. And in this case, the cohomology does not change because Joannalu's device produces homotopy equivalence. Then I can replace spec R prime. That may be a huge thing, and I wanted a reasonably small example. So I'm going to replace spec R prime by spec R using an affine Lefschetz theorem. So Lefschetz hyperplane theorem, so that spec R is of dimension L, and we still have the following property. But once I hit dimension L, I can't go any further. Now, by construction, there was a map from spec R to V mod G. And there's a torsor V over that. I can pull back T to this. And there is a form B associated to T. And that's the form we want. The claim is B cannot be generated by I elements. Oh dear, sorry. I need to add a page here. So let me explain why B cannot be generated by I elements. T has a map to a point, it's equivariant. And UR has an equivariant map to a point. And this gives rise to the following. Sorry, I'm having a mild. There, that's better. This gives rise to a diagram of cohomology groups. Yeah, elf cohomology G equivariant. As by construction, this was set up to be an isomorphism. And this was chosen to be non-zero. This was set up to be 0. And as a consequence, there can be no dotted arrow of the form indicated. And that implies that there can be no map here. But theorem 1 says that any generating R-tuple would give rise to such a map, so none can exist. And that concludes the proof. Okay, so I'm a little bit further behind than I thought I would be. Sorry about that. So let me try to say something about Bert's question very briefly. Right, CR to be the codimension of ZR in A to the R. And this regulates what the best bounds are, it seems. This is what we believe. And we have the following result, which I hope I don't misstate because I'm going slightly faster than I wanted. Let's state I will not prove this. This is theorem 3. If the dimension of R is less than CR, then we know that the number of generators for the R form is bounded by R. On the other hand, so that's the bound in the other direction, about which I will say very little. If we wanted to make theorem 2 as efficient as possible, the method will, so let's say this, the proof of theorem 2 relies on what does it rely on really? It relies on finding an example where HL of BG to HL of UR is not injective. And the earliest point if we're working with complex numbers, the least possible L is actually 2CR. So there's still a gap here between theorem 3, which says CR, and the best possible improvement you could ever hope for in theorem 2, which says 2CR. but we're quite happy to live with that. And then maybe just to conclude, let me say, well, we've devoted, I and some students have devoted some effort to calculating this codimension in as many cases as we had time for. So let me give some instances of this codimension, which seems to regulate the whole story. Really, I just want to advertise the work of some excellent students. In the old case, the first case, the example of Chase, CR is r plus 1 minus n. That's the codimension of the bad locus. And the least known instance, the version of theorem 2 that you get in that case, well, Chase's version is as good as could possibly be, right? So the CR and this thing, they agree in this case, and that's why I put a gold star there. For 2 by 2 matrix algebras, this quantity CR is r minus 1. And the best, this is due to my student, Sebastian Gant. It's beautiful work. The best example, when r is odd, the best you can do is 2r minus 1 currently. And when r is even, it's 2r. That may be improved upon, I'm not certain. Then this is our own work. And then finally, I'd like to say that in a summer research project, I and some undergraduate students, we worked out the examples of algebras with involution. And here we don't know, we can't make an effective version of theorem 2 that's currently any better than what I gave in this talk, but we have done this working out of what that codimension is. So that looks like the theoretical best possible statement for generating in those cases, if we can make it work. Okay, so I'll stop there. Thank you.
Thank you very much. Let's thank the speaker. Wonderful talk. So, is there any question? Any question? Any question? So if you would like to ask question, just switch on your mic and ask it.
Can you say something about the tall algebras?
Yeah, so the answer for tall algebras is joint work between me and Abhishek Kumar Shukla, and there we get the absolute best possible result as well. But the example is essentially that of Chase. So it falls under this heading as well. So I mentioned the tall algebras in the first slide. Perhaps I should put it. So it's the same example essentially, because there's a connection between line bundles and a tall algebras of degree 2, and from there you're off. You can do everything. So I should advertise this is myself and A.K. Shukla. So that's that.
So more questions?
What about Azumaya algebras? Oh, you got that.
Sorry, I muted myself.
Okay,
there.
thank you.
A sip of water. The Azumaya algebras are here. So a shortcoming in this whole business is that we're using everything over the complex numbers, and probably over other fields you can get, you can bring this number here in this third column. These examples, with the exception of the examples of in the first two cases, all over C, except the first two. So I think the theorem can be improved by moving away from the complex numbers, but it's hard.
More questions? More questions? Comments? If not, let's thank a speaker again. So indeed, on behalf on behalf of all organizers, I would like also to thank all the speakers for this summer session, as well as all the participants. So thank you very much. And so we will resume in 2 months in September.
I hope to see you there.
Thank you. Yeah, thank you all, and have a nice holidays or summer and so on. Bye.
Bye.